Back in 2017, a team over at Google Brain quietly published a paper that didn't just move the goalposts for AI, it launched them into a completely different galaxy. This is the story of how they unlocked the era of these colossal, trillion-parameter models, and it all started with one simple but totally profound idea.
For years, this was basically the gospel of deep learning. Now, think of parameters as all the little knobs and dials inside a network's brain that it can tune to learn stuff. The thinking was pretty straightforward. To get smarter models, you just had to cram in more knobs, make them bigger. More parameters meant more brain power, but it also meant a brute force approach that was getting ridiculously expensive.
And this is the killer question. The paper just drops on the table. It sounds like it breaks the rules, right? Like getting something for almost nothing? But, believe it or not, they actually pulled it off.
So here's the game plan. We'll start by looking at the massive wall AI researchers were slamming into. Then, we'll dive into the paper's brilliant solution and the clever engineering that made it all work. After that, we'll check out the jaw-dropping results, trace its legacy all the way to the models we use today, and wrap up with a cool idea about what might be next.
Okay, so let's set the scene. It's the mid-2010s. The entire field is kinda stuck in this simple but totally unsustainable cycle. The logic was ironclad. Make a model bigger, feed it more data, and you get better results. Easy, but the problem was the cost. It was just exploding. Training costs were going up quadratically. That means a model that's 10 times bigger didn't cost 10 times more to train. It cost closer to 100 times more. This whole brute force era was about to hit a very, very expensive wall.
Now, people weren't clueless. They had this idea called conditional computation, basically only using the parts of the network you need for a specific task. But in practice, it was a total nightmare. GPUs are built for doing one giant simple calculation, not for making a ton of tiny if this, then that decisions. It absolutely tanked your training efficiency and created these insane data traffic jams.
So instead of trying to smash their heads through that computational wall, this paper found a really clever way to just walk around it.
And say hello to the mixture of experts layer, or MOE for short. The core idea is just beautiful. Why force one single giant brain to learn absolutely everything from poetry to physics? Instead, why not create a whole library of smaller, specialized expert brains? And then you just add a smart traffic cop, a gating network, to route each problem to the few experts that are best for the job.
So how does this actually work? Well, think of it like a hospital. An input shows up, like a patient coming into the emergency room. The gating network is the triage nurse. It takes a quick look, figures out what's going on, and sends the patient to just a couple of specialists, maybe the heart doctor and the brain surgeon. Only those two specialists do any work, which saves a ton of the hospital's resources. Then their findings are combined for the final answer.
Now, having a great idea is one thing, but actually getting it to work on real-world hardware, that's a whole different ballgame. The team had to pull off some seriously clever engineering tricks to get these experts to play nicely. The first big trick was in that gating network. See, the old way would give a little bit of work to every single expert, which totally defeats the purpose. You don't save any compute. But these authors introduced what they called noisy top K gating. It's ruthless. It just picks the top few experts, say the top 2, and gives them all the work. Everybody else, they do literally nothing. They don't even turn on. The noisy part just helps keep the router on its toes so it doesn't get stuck in a rut.
But this creates a new problem. What's to stop the gating network from just getting lazy? It might find a couple of experts that are pretty good at most things and just send all the work to them all the time. This is a total disaster because all those other experts never get a chance to train while the popular kids get totally overworked.
The solution was just so elegant. They called it a load balancing loss. You can think of it like a tax or a penalty. If the gating network starts playing favorites and sending too much work to one expert, this function kicks in and penalizes the whole model. It's like a little nudge that says, hey, spread the love a little. This is absolutely crucial for making sure every expert gets a chance to learn and become a true specialist.
So, with this incredibly complex system of routers and experts and penalties, did it all actually pay off?
Well, the results were frankly outrageous.
This first chart is basically the magic trick. On the bottom, you have the number of parameters in the model. And on the side, you have test perplexity, which is just a fancy way of saying how confused is the model by new stuff. Lower is always better. And look at this. For the exact same amount of computer power, just by adding more experts, scaling up to billions of parameters, the model got way, way less confused. It got so much better. And this one? This just perfectly illustrates the new world they created. That blue line is the best of the best from the old way of doing things. And the green line? That's their MoE models. It's not even a competition. At every single price point, for any amount of compute you're willing to spend, the MoE models delivered hugely better performance. It wasn't just an improvement, it was a whole new ballgame.
But here's where it gets truly wild. When they fed the model a way bigger data set, we're talking 10 times more data, that performance gap didn't just stay the same. It got wider. This was the ultimate proof. The more data you have, the more these giant, specialized models can learn, leaving the old architectures completely in the dust.
And this wasn't just some theoretical lab result. They put it to the test on the gold standard translation task, English to French. Their 8.7 billion parameter MoE model went head-to-head with Google's own state-of-the-art system, the reigning champ, and it won. And it did it while using less overall computation. Just incredible.
So yeah, this paper didn't just publish some great results and then disappear. It laid down the fundamental architecture for the entire AI world we're living in right now.
I mean, the family tree here is crystal clear. The ideas from this 2017 paper led directly to Google's own monster internal models. Then the idea exploded into the open source community with models like Mixtral 8x7b, and today it is the beating heart of flagship models like Google's Gemini.
In their original paper, the biggest model they trained had 137 billion parameters. Back then, that number was just absurd, outrageous, as they put it. Today, that's practically the price of admission to have a state-of-the-art AI. And this paper is the reason why.
So where does an idea this big go next? This is where we can get a little creative and think about what the core MoE insight might unlock down the road. Let's just push this idea one step further. What if the experts aren't all just different little neural networks? What if one expert is a calculator, and another one is a code interpreter, and a third is a live web search tool? The gating network's job wouldn't be to route a problem to some parameters, but to route it to the right tool. This could be the architectural breakthrough we need to build AI agents that are more reliable, more factual, and way more versatile.
This is for entertainment purposes only.